The process that keeps you alive when you haven't eaten for 3 days or even 3 weeks, that is all about fat.
So our mission today is, I'd say, pretty ambitious. We are not just going to say fat burns for energy. No, we are going to trace the entire life of a single fat molecule
From start to finish.
from the moment it gets the signal to leave, the storage unit on your waistline, how it travels through the blood, how it breaks into the cell, and how it gets turned into just massive amounts of ATP.
We're going to cover every single step, the transport, the activation, the incredibly clever shovel systems, and then what you call the wood chipper mechanism that just chops these molecules to pieces.
And then the really fascinating part, the Goldilocks zone of ketosis.
Right. Why it's a life-saving adaptation for starvation, but also why, if that same system breaks or goes into overdrive, it leads to something called ketoacidosis, which can be fatal in a matter of hours.
High-stakes chemistry. I love it. So let's set the scene. I've just finished a long fast, or maybe I'm deep into a marathon. My body needs fuel. It looks at my adipose tissue, my body fat, and it says, okay, it's time. What's the very first thing that happens?
Well, the very first problem is one of logistics. The fat is stored over there in the adipose tissue, but we need to burn it over here in a muscle or in the liver.
Yeah.
So the fat cells have to release what we call free fatty acids, or FFAs.
Free fatty acids. Okay, and I've also seen them called no-fat, non-esterified fatty acids.
Correct. Same exact thing. It's just a long chain of carbon and hydrogen atoms.
Hmm.
But immediately, the instant they step out of that fat cell and into the bloodstream, they face a crisis.
And that crisis is just physics.
It's pure physics. Blood is mostly water. Fat is hydrophobic. It hates water. If you were to just dump liquid fat into your veins, it wouldn't work. It would just clump together into little oil droplets. You could get an embolism. It would be a complete disaster.
So they can't just swim to the muscle on their own.
No, absolutely not. They need a boat. Or, if we're going to stick with a commute analogy, they need a taxi. And that taxi is a very important protein called albumin.
Albumin, that's the most abundant protein in our blood plasma, right?
It is. It's the absolute workhorse carrier for all sorts of things. So these long-chain fatty acids, they bind very tightly to albumin, and that's how they travel the highway of the circulatory system. The albumin essentially drives them to the tissues that are screaming for energy skeletal muscle, the heart, the liver.
Okay, so the albumin taxi pulls up to the curb of a muscle cell, the fat molecule gets out, it crosses the cell membrane, and now it's inside the cell, just floating in the cytosol, sort of the main living room of the cell. Is it ready to be burned?
Not even close. In fact, if the cell tried to burn it right now, nothing would happen. The fat is, for all intents and purposes, chemically inert. It's asleep.
Okay.
Before we can do anything with it, we have to activate it.
Activate it. How do you activate a fat molecule?
You have to attach a handle to it, a chemical handle that the rest of the machinery can grab onto. We attach a molecule of coenzyme A, or just CoA. This reaction converts the fatty acid into what we call an acyl-CoA.
Okay, so the acyl part just refers to the fatty acid chain itself, and the CoA is the handle.
That's it. But this attachment, this handle, it isn't free. And this is where we see the first big rule of metabolism. You have to spend money to make money.
This is the cover charge to get into the club.
It is the cover charge, exactly. The enzyme that does this is called a silicosynthetase. Though old school biochemists, they love to call it thiokinase.
Thiokinase, that sounds pretty aggressive.
It is. It's a very forceful reaction. It grabs the fatty acid, it grabs a molecule of ATP, our energy currency, and it grabs the CoA. It smashes them all together. But here's the really subtle point that most people miss, and where the source text gets very specific. This doesn't just cost 1 ATP.
Right, because normally when we use ATP, we just break off the N-phosphate. ATP becomes ADP. That's like the standard $1 transaction.
Correct. But thiokinase is a high roller. It doesn't just pop off the N-phosphate. It rips off the last 2 phosphates together as a single unit.
Whoa. So it doesn't go from ATP to ADP. It goes all the way down to AMP, adenosine monophosphate.
Exactly. It releases a 2-phosphate chain called pyrophosphate, or PPI.
So in energy terms, that's the equivalent of spending 2 molecules of ATP. We've paid double the usual price just to get started. Why so wasteful?
It's not waste at all. It's insurance. This is a brilliant little bit of thermodynamics. That pyrophosphate, the PPI that floats away, it is immediately targeted by another enzyme in the cell called inorganic pyrophosphatase.
And what does that enzyme do?
It destroys the PPI. It shatters it into 2 separate individual phosphates.
It's destroying the evidence.
It is. By destroying one of the products of the reaction immediately, it makes the whole activation process completely irreversible. The cell is burning the bridge behind this fatty acid. It's making a commitment. It's saying, we have spent this significant energy, we have activated this fat, there is no going back, you are now committed to being burned.
I see. Because if the PPI was just floating around, the reaction could maybe drift backward if the concentrations changed, but by destroying it, you're locking the door behind it.
You've locked it, you've thrown away the key. So now we have acyl-CoA. It's activated, it's expensive, it's floating there in the cytosol. But we have a new problem, a geographical problem.
Let me guess. The machinery to actually burn the fat, the furnace, is not in the cytosol.
Correct. The furnace, the whole beta oxidation machinery, is deep inside the mitochondria, specifically in the mitochondrial matrix.
Okay, so can it just walk through the door? I mean, mitochondria have membranes?
2 membranes. The outer one is pretty porous, so the acyl-CoA can slip through that, no problem. But the inner mitochondrial membrane, that thing is Fort Knox. It is arguably the most selective, most secure barrier in the entire human body.
And I'm guessing acyl-CoA is not on the guest list?
It is absolutely not on the list. The inner membrane is completely impermeable to acyl-CoA. It just bounces off. It can't get in.
So we have a situation, we have the fuel, we've paid the expensive activation fee. The furnace is literally nanometers away, right on the other side of this wall. But we're locked out.
We're locked out. And this is where we need the carnitine shuttle.
Carnitine. Okay, I feel like I see this on the shelf at supplement stores all the time. Fat burner. Metabolic enhancer. This is the actual mechanism they're trying to leverage.
This is the mechanism, yes. Carnitine, and if you really want to impress your friends, it's beta-hydroxy-gamma-trimethylammonium butyrate is a molecule that's found everywhere, but it's especially abundant in muscle. And it functions essentially as a specialized shuttle bus to get across that impermeable membrane.
But it can't just be a simple ride, can it? You can't just hop on the back of a carnitine molecule.
No, it's more sophisticated.
Yes.
It's like a badge swap at a security checkpoint. It's a relay race, really, that involves 3 specific players.
Okay, let's break them down. Player 1.
Player 1 is an enzyme that's sitting on the outer face of that inner membrane. It's called carnitine palmitoyl transferase I. For short, we just call it CPTI.
CPTI, the gatekeeper.
The gatekeeper, perfect name for it. CPTI grabs our acyl-CoA, it rips off that expensive CoA handle we just paid for, and it immediately replaces it with a carnitine molecule.
So now, instead of acyl-CoA, we have acylcarnitine.
Right. It's swapped the ID badge. The CoA badge doesn't grant you access, but the carnitine badge, that gets you through the next door.
Okay, so now we have acylcarnitine. Does it just drift through the membrane?
No, it needs a specific door. Player 2 is a transporter protein that's embedded right in the membrane, and it's called carnitine acylcarnitine translocase. It's basically a revolving door.
Yeah.
It grabs the acylcarnitine from the outside and spins it into the matrix.
But a revolving door has to work both ways. If something goes in, something else has to come out.
And something does. Free, empty carnitine comes out.
Sure.
It's a perfect one-for-one exchange. One loaded fat molecule goes in, one empty shuttle bus comes out to pick up the next passenger.
Very efficient. Okay, so now the fat is inside the matrix. We are in the holy of holies. But wait, the furnace machinery, that uses the CoA handle, right? But now we're holding a carnitine badge. We have the wrong tool for the job.
Exactly. We have the wrong handle again. So we'd player 3, carnitine palmitoyl transferase 2, or CPT2.
Which is located on the inside of the membrane?
On the inside, exactly. And it does the exact reverse of the first enzyme. It grabs the acylcarnitine, rips off the carnitine, and slaps a new CoA molecule back on.
So after all that, paying the cover charge, swapping the badge, going through the revolving door, swapping the badge back, we are exactly where we started, chemically speaking. We have acetyl-CoA again. But the crucial difference is, now we are inside the furnace.
It seems like a ridiculous amount of work just to move a molecule a few microscopic inches. But that shuttle, specifically CPTI, that first gatekeeper, is the single most important regulatory point in all of fat metabolism. If that door was just always open, your metabolism would be chaos. The body has to be able to lock that door.
And we're definitely going to come back to who holds the key to that lock. But for now, we're in. The fat is in the matrix. It's time to burn. And this is the process called beta oxidation.
Beta oxidation. The wood chipper.
I love that image. Because you've got this long chain of carbons. Let's say it's 16 carbons long. And we aren't burning it all at once, like a log in a fireplace. We're chipping away at it.
2 carbons at a time. It's methodical. We chop off a 2-carbon piece, then we push the rest of the log forward. Chop off another 2-carbon piece, push it forward again.
And why is it called beta oxidation? What's so special about the beta position?
Because all the chemistry, all the action happens at the beta carbon. So if you're counting from the CoA handle, the first carbon is the carboxyl carbon. The next one's called alpha, that's carbon number 2. and the one after that is beta, carbon number 3. We are going to make our cut between the alpha and the beta carbons.
So we're aiming to snip the chain between carbon 2 and carbon 3.
That's the target. And it's not just a simple snip. It's a repeating 4-step cycle. And we should really go into the weeds here because the chemistry is just, it's beautiful.
Let's do it. Let's zoom in. We're down at the atomic level now. We are staring at that bond between the alpha and beta carbons. What is step 1?
Step 1 is dehydrogenation. We need to weaken that area, destabilize it. So an enzyme called acyl-CoA dehydrogenase comes in. It acts like a piece of biochemical Velcro. It just rips 2 electrons in the form of 2 hydrogen atoms right off the chain.
Right.
One from the alpha carbon, one from the beta.
It just strips them naked.
Pretty much. And those high-energy electrons, they have to go somewhere. They're immediately caught by a cofactor, a little electron bucket called FAD, and that FAD becomes FADH2.
And FADH2, that's energy, right? That's a charged battery that can be used later.
It is. That little battery goes straight to the electron transport chain to make ATP. But look at what's left of the fat molecule. Since we ripped those hydrogens off, the alpha and beta carbons are now unstable. To stabilize themselves, they're like 2 people who have to hold hands to stay upright. They form a double bond.
A double bond. The product is called delta-2-transinyl-CoA.
Correct. So now, step 2. You can't just chop a double bond with a simple axe. We need to weaken it even more. We need to soften the wood before we cut.
And how do we soften it?
We hydrate it.
Okay.
Step 2 is hydration. The enzyme is enoyl-CoA hydratase. It takes a molecule of water H2O and it forces it right across that double bond.
So chemically, we're just jamming a water molecule into the structure.
We split the water, we put the hydroxyl group, the OH, onto the beta carbon. And this is very strategic. That oxygen atom is going to be the handle that we grab onto for the next step.
So we've gone from a tough, straight hydrocarbon chain to something that has a chemical soft spot and alcohol group sitting right on that beta carbon.
Precisely. The product is called L3-hydroxycyl-CoA. Now we're ready for step 3. We attack that soft spot we just created.
Another oxidation, I'm guessing?
Yes. The enzyme is L3-hydroxycyl-CoA dehydrogenase, and we're going to steal 2 more hydrogens. Specifically, we're going to steal them from that alcohol group we just added.
And who catches the electrons this time?
A different cofactor.
Yeah.
NAD plus kinome. It swoops in, grabs the hydrogens, and becomes NADH.
And NADH is an even stronger battery than FADH2, isn't it? It's worth more ATP.
It is. NADH packs a bigger punch. But again, look at the molecule. We strip the hydrogen off that alcohol group. That turns the COH single bond into a CO double bond.
Which is a ketone group.
The ketone group, hence the name 3-ketoacyl-CoA. Now just picture this structure. You've got the CoA handle, you've got the alpha carbon, and now the beta carbon has this double bonded oxygen pulling electrons away from it. That bond between alpha and beta is now incredibly stressed. It's trembling. The electrons just being pulled in too many directions at once.
It's ready to snap.
It is begging to be cut. And that brings us to the final step, step 4, the guillotine.
Thiolysis.
Thiolysis. The enzyme is thiolase. Brings in a brand new sharp molecule of CoA, and it swings that CoA like an axe right into that trembling bond between the alpha and beta carbons.
Crack.
The chain splits in 2. The first 2 carbons, that's the alpha carbon and the original carboxyl carbon, they fall off as a 2-carbon molecule called acetyl-CoA.
And acetyl-CoA is the gold standard of fuel. That goes directly into the citric acid cycle to make a ton of energy.
Exactly. And what's left? The original fatty acid chain. But now it's exactly 2 carbons shorter. And that new CoA molecule used as the axe, it's now the new handle for this shorter chain.
So it's perfectly primed to go right back to the beginning of the cycle. Step 1.
Immediately, it re-enters the top of the wood chipper. Dehydrogenation, hydration, oxidation, thiolysis. Chop. Another acetyl-CoA falls out. The chain gets 2 carbons shorter, and you just rinse and repeat until there's absolutely nothing left.
Okay, I want to do the math on this because the textbook gives us a balance sheet, and the numbers are just staggering. Let's use palmitate as our example. It's the most common fatty acid in humans. It's 16 carbons long.
All right, let's do it. Palmitate is C16. We're chopping off 2 carbon units at a time. So how many chops does it take to finish the log?
Well, 16 divided by 2 is 8, so 8 chops.
Careful. It's a classic trick question. Imagine a baguette. You want to cut it into 8 equal slices. How many times do you have to cut it with a knife?
Ah, I see what you did there. The last cut gives you the 7th piece and the 8th piece at the same time, so it only takes 7 cuts.
7 cycles of the wood chipper, exactly.
Yeah.
So for palmitate, we run the cycle 7 times. That means we're going to generate 7 molecules of FADH2 from step 1 and 7 molecules of NADH from step 3.
Okay. And for our output, we produce 8 molecules of acetyl-CoA, the 8 slices of the baguette.
Perfect. Now let's turn all of that into our final currency, ATP. The numbers can vary slightly, but the standard values are that each FADH2 gives us about 1.5 ATP. So 7 times 1.5 is 10.5 ATP.
10.5. Got it.
And each NADH gives us about 2.5 ATP. So 7 times 2.5 is 17.5 ATP.
Okay, so that adds up to 28 ATP just from the chopping process itself.
Just from the chipping. But the real money, the big payout, is in the slices.
Yeah.
The acetyl-CoA, yes. Each of those 8 acetyl-CoA molecules goes into the citric acid cycle, and each one of those turns generates a massive 10 ATP. So 8 times 10 is 80 ATP.
So 80 ATP from the acetyl-CoA plus the 28 from the chipping process. That's 108 ATP.
That's our gross yield. But don't forget the cover charge.
Ah, right. The activation step way back at the beginning in the cytosol, the biokinase. We had to spend the equivalent of 2 ATP to get this whole party started.
So we take our 108, we subtract that initial investment of 2, and our net yield is 106 moles of ATP from a single mole of palmitate.
106. That is huge. I mean, compare that to a molecule of glucose. Glucose gives you what, maybe 30, 32 ATP?
Exactly. This is why fat is such a dense form of energy storage. If you look at the raw thermodynamics, the complete combustion of palmitate releases about 3,200 kilojoules of energy. Our bodies capture about 33% of that as usable chemical energy. For a biological machine that's running at 37 degrees Celsius, that is remarkably, stunningly efficient.
It's an absolutely beautifully tuned engine. But, engines can jam. The wood chipper works great for standard logs, straight chains, even number of carbons. But nature is messy. What happens when we throw something weird into the chipper?
The special scenarios. The text highlights 3 main situations where the standard chipper gets stuck.
Okay, scenario A, odd chain fatty acids. Most of the fats we have are even numbered 16, 18 carbons. But sometimes from our diet, we get odd ones, 15 carbons, 17 carbons.
Right, so the wood chipper starts up, chop, chop, chop. 2 carbons, 2 carbons, 2 carbons. And at the very, very end, you're left with a little 3-carbon nub.
You can't split a 3-carbon piece into 2.
No. That 3-carbon piece is called propionyl-CoA, and the body has a special separate pathway for this. It takes a few steps, but it converts that propionyl-CoA into a molecule called succinyl-CoA.
And why does that matter? What's special about succinyl-CoA?
This is a huge aha moment for biochemistry nerds, because we have this golden rule that gets drilled into our heads. You cannot turn fat into sugar.
Right, because acetyl-CoA, the main product, cannot be turned back into glucose. It's a one-way street.
But succinyl-CoA can. It enters the citric acid cycle at a point where it can be siphoned off to make new glucose, a process called gluconeogenesis. So that little 3-carbon propionyl residue from an odd-chain fatty acid is the only part of any fat molecule in your body that is glucogenic, the only part that can be turned into sugar.
Wow, so that's the one exception to the rule. If you are truly starving, that tiny 3-carbon piece is the only part of your vast fat stores that can directly help refill your blood sugar.
That's the one. Now, scenario B. The so-called healthy fats, unsaturated fats.
Olive oil, canola oil, the stuff that has double bonds in the chain.
Right. And the problem's a shape. Saturated fat is like a perfectly straight stick. But an unsaturated fat has a kink or a bend in it where the double bond is.
Yeah.
And in nature, that double bond is usually in the cis configuration.
And the wood chipper, the enzymes, they're designed to handle a straight trans configuration.
Exactly. So the enzyme moves down the chain and it gets to that kinked cis bond and it just jams. It's like error, cannot process, and the whole beta oxidation process grinds to a halt.
So we need to call in a mechanic.
We have an on-call mechanic. It's an enzyme called an isomerase. If you want the full name, it's delta-3-cis, delta-2-transenoyl-CoA isomerase.
That is a mouthful.
It is, but its job is simple. It basically grabs that double bond, shifts it 1 carbon over, and twists it from the cis shape to the trans shape. It straightens the log out.
And once the log is straight,
the wood chipper restarts and continues on its merry way. No energy is lost. It's just a quick, on-the-fly realignment.
And finally, scenario C, the monsters. Very long-chain fatty acids. We're talking 20, 22 carbons and up.
These are like giant redwood logs. They literally do not fit into the mitochondrial transport system.
Yeah.
The CBTI gatekeeper looks at them and just says, nope, too big, you can't come in.
So where do they go if they can't get into the main furnace?
They get sent to a different processing plant entirely, a little organelle called the peroxisome.
Peroxisomes. Right. These are the little cellular compartments that usually deal with toxins and things like that.
Yes. And they have their own sort of modified beta oxidation pathway, but it's a much rougher, cruder cut. For instance, in the mitochondria, that first step captures energy as FADH2. In the peroxisome, They don't bother capturing it. They pass those high-energy electrons directly to oxygen.
And what does that make? Oxygen plus high-energy electrons,
Oxygen peroxide, H2O2.
that's bleach. That's highly toxic to the cell.
It is, which is why peroxisomes are absolutely stuffed with an enzyme called catalase, which instantly detonates any H2O2 into harmless water and oxygen. The process produces a lot of heat, but no ATP.
So burning very long-chain fats in the peroxisome generates heat, but not usable fuel.
Precisely. It's energetically inefficient. But the goal here isn't to make energy. The goal is just waste management and pre-processing. The peroxisome chops this huge redwood log down to a more manageable size, usually down to octanoyl-CoA, which is 8 carbons. Then it ships those smaller, more manageable logs over to the mitochondria to be burned properly for ATP.
It's a whole metabolic supply chain. I love it. Okay, so we've mastered how to burn fat. We are cranking out ATP, but the chapter takes a really hard left turn here. What happens when we burn too much fat too quickly?
We enter the world of ketogenesis.
The source material calls this section the liver's altruism. That is such a poetic phrase for a biochemistry textbook.
It is, but it's remarkably accurate. So let's set the stage. You're starving.
Yeah.
Or, alternatively, you are a type 1 diabetic who has no insulin. In either case, your body is screaming for energy. You have unlocked the floodgates of your fat stores. The liver's just taking in massive amounts of fatty acids and chopping them into acetyl-CoA at a ferocious rate.
So the liver is literally flooded with acetyl-CoA. Now, normally, that acetyl-CoA would just go into the citric acid cycle?
Normally, yes. But here is the critical catch. To run the citric acid cycle, the acetyl-CoA needs a partner molecule to combine with. That molecule is called oxaloacetate.
Okay.
But because you are starving, your liver is also desperately trying to make glucose to keep your brain alive, that process of gluconeogenesis. And to do that, it has to steal all the available oxaloacetate.
So the citric acid cycle is stalled. It's missing a crucial part. It's like an assembly line where one of the workers has gone home.
Exactly. So now you have this metabolic dam building up. Acetyl-CoA is just piling up and piling up. It has nowhere to go. So the liver says, okay, time for plan B. If we can't burn these, let's stick them together and ship them out.
It's almost like it's reversing the wood chipper.
In a sense, yes. It takes 2 acetyl-CoA molecules and condenses them to make acetyl-CoA. Then it adds a third acetyl-CoA using an enzyme called HMG-CoA synthase. This makes a key intermediate called HMG-CoA.
HMG-CoA. Wait, that's the intermediate for making cholesterol. Statin drugs work by blocking HMG-CoA reductase.
The very same molecule.
Yeah.
A critical branch point in metabolism. But here in the mitochondria, a different enzyme, HMG-CoA lyase, splits it to form our very first ketone body, which is called acetoacetate.
Acetoacetate.
From here, acetoacetate has 2 possible fates. It can spontaneously decompose, it's a bit unstable, and lose a molecule of CO2 to become acetone.
Acetone, as in nail polish remover.
The very same. It's a volatile solvent. You can't use it for energy. It just dissolves into the blood, goes to the lungs, and you breathe it out. If you walk into an emergency room and you smell a fruity or chemical scent on a patient's breath, that is acetone escaping from their lungs. It's a dead giveaway for very high ketosis.
And what's the other path for acetoacetate?
The other path is that it can be reduced. It can capture some electrons from NADH and become D3-hydroxybutyrate. This is actually the most stable and most abundant ketone body you'll find in the blood during ketosis.
Okay, so the liver has made these 2 main ketones, acetoacetate and 3-hydroxybutyrate. Why is this considered altruism?
Because the liver goes to all the trouble of making them, but it cannot use them for fuel itself.
It cooks this entire meal but can't take a single bite.
It's physically incapable. To burn a ketone, you need a specific activation enzyme. It's called succinyl-CoA acetoacetate-CoA transferase. A better name for it is just thiophorus.
And the liver just doesn't have it.
The liver has 0 thiophorus. It is genetically programmed to lack this one specific enzyme, and this is a design feature, not a flaw. It ensures that the liver cannot consume the very fuel it's producing. It forces the ketones to flow out into the blood to feed the rest of the body.
And when we say the rest of the body, we are primarily talking about the brain.
This is the critical life-saving part. We all know the brain is a glucose hog. It demands glucose. But we also know that those long-chain fatty acids, the ones riding on the albumin taxi, they cannot get into the brain.
The blood-brain barrier. It's like the world's most exclusive nightclub with the strictest bouncer.
Exactly. Albumin is way too big to get in. And the free fatty acids themselves are too dangerous to just be floating around free in the brain. So the brain is chemically cut off from the body's largest energy reserve, our fat stores. If we didn't have ketones, humans would die of hypoglycemia within just a few days of starvation.
So the ketones are the biological workaround.
They are the ultimate hack. Ketones are small, they're water-soluble, they don't need a taxi, they just dissolve in the blood like salt. And they have special transporters that allow them to walk right through the blood-brain barrier.
And the brain does have the enzyme, the thiophorus, to burn them for fuel.
Yes. In a state of prolonged starvation, the brain will switch from being almost 100% glucose dependent to getting up to 75% of its total energy from ketone bodies. It's an absolutely essential adaptation that preserves the precious little glucose we have left. It's an evolutionary miracle, really.
It truly is. But, like any powerful engine, this system needs a break. We don't want to be in ketosis all the time. We certainly don't want to be burning fat if we just ate a large pizza.
Regulation. This is, in my opinion, the most important part of this entire chapter for understanding modern health and disease. How does the body decide? Burn fat or store fat?
It can't just be random. There has to be a switch.
There is a master switch. And that switch is located right at the CPTI door, that gatekeeper bouncer we talked about at the very beginning.
The enzyme that swaps the CoA badge for the carnitine badge.
Right. Just think about it logically. If CPTI is active, the door is open, fat goes into the furnace, and it gets burned. If CPTI is inactive, the door is locked, fat stays in the cytosol, and it gets packaged up for storage.
So what, or who, turns CPTI off? What's the key that locks that door?
A single, incredibly important molecule called malonyl-CoA.
Okay, let's unpack malonyl-CoA. Where does it come from?
It comes from carbohydrates. It comes from glucose. When you eat carbs, your blood sugar goes up, and your pancreas releases insulin. Insulin tells your cells to take in that sugar. They break the sugar down to acetyl-CoA. But if you have too much energy, if your ATP levels are already high, the cell decides to start building fat for storage. And the very first step of building new fat is turning that acetyl-CoA into malonyl-CoA.
Okay, so malonyl-CoA is basically a signal that means we have plenty of energy from carbs and we are now in fat-building mode.
That's exactly what it is. And here is the simple elegance of the system. Malonyl-CoA physically binds to the CPTI enzyme and shuts it down. It inhibits it.
Oh, I see. It's a safety interlock. If the factory is in build mode or synthesis, it automatically locks the door to the incinerator mode or oxidation.
Precisely. Because it would be metabolically insane to be building fat and burning it at the exact same time. It would just be a futile cycle, wasting energy. So let's trace it. High insulin leads to high malonyl-CoA, which leads to CPTI being locked, which means fat burning is stopped, Peter.
And the reverse must be true.
In starvation, insulin levels are very low, so malonyl-CoA levels plummet to near zero. CPTI is now unlocked, the inhibition is released, and the door swings wide open for massive amounts of fat to enter the mitochondria and be burned.
So that one simple molecule, malonyl-CoA, is the ultimate decision maker.
It is the switch.
Yeah.
And just hold on to that thought because it has profound implications for our modern diet and lifestyle.
We will definitely get there. But first, we have to look at the wreckage. Section 6, clinical aspects. Because when any one of these dozens of enzymes breaks, the results are absolutely devastating.
Yeah, these aren't just abstract textbook examples. These are human tragedies that, in many cases, taught us how the pathway actually works.
Let's start with the one with the most vivid name, Jamaican vomiting sickness.
A classic medical mystery. It's caused by eating the unripe fruit of the ackee tree, which is native to West Africa, but is also the national fruit of Jamaica.
The fruit itself is toxic.
Only when it's unripe. When it's unripe, it contains a potent toxin called hypoglycin.
And what does hypoglycin do to our metabolism?
It's what's known as a suicide inhibitor. It gets metabolized in the body into a compound that permanently binds to and inactivates acyl-CoA dehydrogenase.
Wait, that's step 1 of the wood chipper? The very first enzyme in beta oxidation?
It jams the very first gear in the entire machine. And the result is you cannot burn fat at all. The entire pathway is blocked at the very beginning.
And if you can't burn fat for energy,
your body panics. It burns through every last scrap of glucose it has in a matter of hours. You develop profound, severe hypoglycemia. Your blood sugar crashes to fatal levels. It leads to vomiting, convulsions, coma, and often death. All because one single enzyme in this long chain was jammed.
That is absolutely terrifying. What about genetic defects like carnitine deficiency?
This can happen in newborns, especially preemies who can't synthesize enough of it, or due to genetic mutations in the carnitine transporter itself.
Okay.
And if you don't have enough carnitine or the transporter is broken, you have all the fuel in the world, the fat, but you have no way to get it into the engine.
And the symptoms would be?
Muscle weakness is a big one because muscles rely so heavily on fat for fuel. And again, severe hypoglycemia, because if you can't burn fat, you are forced to overconsume your sugar reserves, and they run out very quickly.
And then there are the peroxisomal disorders you mentioned earlier, Repsom disease.
This is a really specific defect in something called alpha oxidation. Remember how we said that phytanic acid, which comes from dairy and beef fat, has a little methyl group branch on it that blocks the normal beta-oxidation wood chipper?
Right, the branch on the log that needs to be shaved off first.
Right. That shaving process is alpha oxidation.
Hmm.
People with Refsum disease are genetically unable to do it. So phytanic acid just builds up and up in their nerves and brain.
Resulting in what?
It's a neurologic disaster.
Right.
Retinitis pigmentosa, which leads to blindness, peripheral neuropathy, nerve damage, and the only treatment is a very strict diet. Avoid all ruminant fats and even some green vegetables that contain phytol.
And Zellweger syndrome.
That's the absolute worst-case scenario. It's a genetic condition where babies are born with no functional peroxisomes. The organelles are just empty ghosts. They can't process any very long-chain fatty acids at all. They accumulate in the brain. It's almost always fatal within the first 6 months of life.
It really just highlights how incredibly fragile this whole machinery is. But we have to end the clinical section with the big one. The one that every doctor, every ER physician fears. Ketoacidosis.
And you need to draw a very sharp, very clear line here. There is nutritional ketosis, which happens during starvation or on a ketogenic diet, and then there is diabetic ketoacidosis, or DKA. One is a controlled, life-saving burn. The other is a raging, out-of-control wildfire.
Explain the difference. What's the key mechanical difference?
In starvation or on a well-formulated keto diet, your insulin levels are low, but they are not zero. You always have a tiny bit of insulin around, and that's just enough to keep the adipose tissue from going completely crazy. Lipolysis, the release of fat, is elevated, but it's still regulated. Ketone levels in the blood might get up to 2, 3, maybe 5 millimolar.
And that's a safe, usable fuel level.
That's fuel. But in type 1 diabetes, the pancreas has failed. Insulin production is zero.
Which means there is absolutely no brake on the adipose tissue.
None whatsoever. The fat cells think the world is ending. They think you are starving to death. So they dump their entire payload of fatty acids into the blood all at once. Lipolysis goes to 100%, completely uncontrolled.
And the liver just gets overwhelmed.
The liver gets hit with a tsunami of fat. And since there's no insulin, the hormone glucagon is sky high, which means malonyl-CoA is zero. The CPTI door is jammed wide open. The liver is essentially force-fed fat, and it has no choice but to churn out ketones at an absolutely impossible, unsustainable rate.
And the levels in the blood go up to what?
Not 5 millimolar, they go to 20 millimolar,
Oh,
25 millimolar.
And as we said, ketone bodies are acids. Cetoacetic acid, beta-hydroxybutyric acid.
Exactly. They flood the blood. They completely consume the body's natural bicarbonate buffer system. And the blood pH starts to crash. The blood itself becomes acidic.
Which denatures proteins. It stops enzymes from working.
It shuts down the entire body. It's a catastrophic metabolic acidosis. This is a life-threatening medical emergency. The patient is severely dehydrated, they're breathing very rapidly, trying to blow off CO2 to compensate, and their breath smells like acetone.
So the very same mechanism that was designed to save us in starvation ketogenesis becomes the weapon that kills us if the primary regulatory signal, insulin, is completely cut.
It's all about balance. The difference between a medicine and a poison is always the dose.
So let's try to wrap this all up. We have been on quite a journey. We started with a single fat molecule riding an albumin taxi. We paid the expensive 2 ATP cover charge to get activated. We swapped our badges at the CPTI security checkpoint. We went through the 4-step wood chipper. We saw the liver's incredible altruism in feeding the brain.
It's an absolutely incredible, elegant system.
What's the biggest picture takeaway for you from all this?
For me, it's the sheer interconnectedness of it all. We tend to think of our organs as separate little buckets. But this story shows the adipose tissue in constant conversation with the liver literally sacrificing its own ability to eat in order to feed the brain. The muscle acting as a massive energy sink. It's not a collection of parts. It is a single, distributed, intelligent network.
And for me, I can't stop thinking about malonyl-CoA.
The master switch.
Just think about the world we evolved in, a world of scarcity. We needed a switch that was exquisitely sensitive, a switch that said, the second food is here, the second insulin is present, LOCK, the fat-burning door immediately, and hoard every single calorie you can.
That programming is what saved our ancestors from starvation.
But now, we live in a world of caloric abundance. of constant snacking. For the average person eating a standard Western diet, insulin is elevated from the moment they wake up until the moment they go to bed.
Which means, biochemically, malonyl-CoA is high all day long, which means CPTI is inhibited all day long.
The door to the furnace is locked shut. We are metabolically hardwired by millions of years of evolution to not burn fat in the modern food environment. That ancient life-saving safety valve might be the single biggest biochemical root cause of the modern obesity epidemic. We are pushing against our own fundamental programming every time we try to lose weight in a high-carb world.
That is a very sobering but scientifically sound way of looking at it. We are running Stone Age software on 21st century hardware.
And the engine is flooding. Well, on that cheerful thought, thank you for diving deep with us.
Always a pleasure.
Next time you feel a hunger pang, just take a second and remember, that's just your liver getting ready to be altruistic. We'll see you next time.